Okay. Our next speaker is going to be Hubicki, so I'm very excited to have him giving a talk today. He's an assistant professor of mechanical engineering at Florida State University, and he's also with the Florida A&M and FSU College of Engineering. Christian directs the Optimal Robotics Lab, and his research specializes in bipedal locomotion, specifically optimization methods that apply to both legged robotics and biomechanics. So with that, I'm really excited to hear. Take it away.
Well, thank you so much for the introduction. Thank you. And thank you so much for inviting me and organizing this safety workshop. This is very exciting for me, I have to admit. And I'm also additionally honored to follow my postdoc advisor, Aaron. I guess it's always a tough act to follow your excellent, well-established advisor, but it is really an honor to be here alongside him. So, as was mentioned, my name is Christian Hubicki. I'm an assistant professor at the FSU College of Engineering. It's actually a unique college of engineering that is a joint college between Florida State University and Florida A&M University, which is a historically Black college and university. So it's a really fascinating program I encourage you to look into. And that's all in Tallahassee, Florida. That's the one in Tallahassee, not Gainesville. I get it all the time. It's all right. And I especially want to thank the Toyota Research Institute, who was a major funder of all this work. This is all fairly recent stuff we've been getting into in the last year or so, and they were so kind as to fund this idea of looking into learning and adapting to novel failures. So in terms of my background isn't sort of in safety critical systems per se. My background is in legged locomotion. This was some of my PhD work here, along with several of my colleagues, on this robot Atreus. It's a bipedal walking robot. We had it walking blindly over terrain in front of a live audience, which anyone here who's done live robot demos, Godspeed to you. And so a lot of my background was in legged locomotion, and currently in my lab we are finding ways to make robots a bit more robust and efficient in moving around. This is my student Jason literally pulling the rug out from underneath our CASI robot and catching itself. But a lot of bipedal locomotion, legged locomotion in general, a lot of these techniques have at their core some kind of motion planning. Right. When I say motion planning, I mean trajectory optimization. So something that is at least partly in a continuous time domain, if not a hybrid domain with discrete events. Lots of those. So those are the kind of dynamics that I'm talking about here. So my timer, so I don't go too far over time. All right. And so at the core of a lot of these methods, there will be something that looks like a deterministic trajectory optimization, where you'll have some objective function to be defined by you. Sometimes there's an art to that. We try to eliminate that art wherever we can, and subject to a bunch of dynamical constraints and or task or path constraints, terminal constraints, choose your constraints, whatever constraints you want. Theoretically, your NLP can solve it. If it's convex, it definitely, almost certainly, hopefully can. So now, what this does in a lot of locomotion is that you will put in a model of your robot, and out will pop out a trajectory optimization, these trajectories that more or less guide the motion. And there are lots of formulations for including motion planning into robot control, and they'll come out looking something like this after much tuning and crafting of the controller, right? So, and in my heart of hearts, I kind of love motion planning and trajectory optimization. So you have an understanding of where I come from with this upcoming method. And I'd like to apply to different modes of locomotion as well. I love to plug two of these ICRA papers that I'm happy to be on with my students and colleagues here. Please check those out. They worked really hard on those. But what inspired my work on novel failures and adapting to them wasn't any of these robots. It actually was my collaborative work with this scientist here, Monica Daly. She is a biomechanist, and one of her key research subjects is guinea fowl, birds. And they're amazingly agile runners that it's actually running over a little pothole like there, but it's not even there. It's incredible. It's this inspiration for a lot of the robotics that were involved in my PhD dissertation and many others as a great template for stable and agile locomotion. And why was I involved with this project? In fact, here's me with my research subject right here, just for comparison. I work with robots, but the answer is I was involved in using motion planning to try to understand how these birds are as good at moving around as they are. What do they care about? And if we knew what they, hypothetically, if we knew what they cared about, we could formulate a trajectory optimization and reproduce and or predict their locomotion. So here's an example of just a trajectory optimization of us trying to get a simple bird model rounding a turn. And it's right now it's optimizing using a nonlinear programming solver to come up with a trajectory that says, oh, good, cut the corner, that's a smart idea, that's great. We would add in certain constraints, right? Things about the safety for our locomotion. What's a big one for bipedal locomotion? What don't we want the robot to do? Anyone in the audience? Fall over, yeah, you're exactly right. Congratulations to you. That's exactly the right answer, right? So you don't want them to fall over, right? So naturally we put that as a constraint in our optimization, something we don't want to do. So we did this kind of optimization analysis, and Monica set up some experiments, you know, of a bird trying to turn around a corner. And we would put the bird in here and we kind of encourage it to go. And you'll notice something really quick. I'll replay it so you can see it right there. Watch this. It sort of slips, right? So it slips and falls on the ground, right? Clearly it's fine. It's okay. It's all right that it fell on the ground. That's okay. And you might say, yeah, but it didn't mean to do that. It's an accident, you know, that slipped and fell. Well, you know, thankfully, our biomechanist colleagues are really great at setting these experiments up in a way where they try to isolate whether or not the bird seems to prefer falling or not, or will try not to fall. And the way that she set this experiment up, there wasn't a strong preference that for not falling in this scenario. You know, falling wasn't a huge deal for it. What was more important was getting away from the experimenter. So, I mean, you never know what they're going to look like. I mean, you know, it could be very scary, right? So the point is, the mode of failure is a fluid concept in nature, and also in our robots. There are so many ways that our robots can fail. And of course, we have to incorporate them all. And the question is how? And I think we saw a wonderful talk by Aaron on how to use control barrier functions for this process, okay? And I'm going to talk about a somewhat different approach, where I want to incorporate modes of failure and into deterministic motion planners. So that way so you come up with these motion plans on the fly, hopefully, so that way you can decide the fall if it's a good idea. We're not there yet, just as a spoiler, but there could be a lot of hope. This took me in a lot of different directions I didn't expect to go. There's a lot of robots I never thought I'd be working with. So prepare yourself for that coming up. So our goal is to extend our motion planners to, one, emergently prioritize many sources of task failure, okay? And we're going to colloquially call them risks, okay? I'm not going to make grand claims about risk as a metric or a measure. That's not what I'm talking about. I'm going to be talking about probabilities of failure. That's what I mean in the context of this talk, okay? And we want to adapt to novel failures as they happen, okay? So we're going to want some kind of low shot learning. You know, we don't want to fail 1,000 times to understand how to not fail again. And we want to be able to learn and re-optimize in real time on the fly. So we need our motion planners to be fast, preferably somewhere in the millisecond range, right? So we're talking convex LQPs or LPs if possible. Would be lovely to get. And my big picture goal is I want like complete task improvisation. If something changed that made you fail your task, you should be able to say, I understand the implications of that and behave entirely differently as a consequence. So what I want is for the probability of failure to shape solutions for our optimizations. And again, I'm considering probability of failure. I'm colloquially calling it risk. All right. But why probabilities? Why am I focusing on probabilities? Well, I'll give two big reasons. One is it's a good one-to-one way to measure this bad thing can happen, this bad thing can happen. How do I split the difference? If you're putting it in a cost function, you might put a weighting factor on that, right? You say, I care a little bit more about this than that. And that's fine. But what does that weighting factor really mean? What are the units of that weighting factor? I perish the thought, you know, but so that this allows a one-to-one comparison that way, okay? And number two, probabilities are theoretically and practically measurable, okay? I stepped on that puddle 10 times, I fell once, you know, I measured it imprecisely as a 10% chance I'm gonna slip in that puddle, okay? So something I can learn from my experience in the field. So we put together this diagram here, which I don't know, so I spent too much time and escape on it, but I'm proud of it. But basically the idea is you have some set of locomotion capabilities that you have, also the demands of your task fundamentally, but then you'll also have some risk landscape, these probabilities for which you are likely to to succeed or fail, okay? And you could have some level set in there, which is your acceptable risk tolerance, or you could say, I want to minimize my risk, okay? Those are two different ways to handle this in the big scheme of things, okay? And we want to put these all into a deterministic optimization because they tend to run pretty fast. So let's move on to motion planning with risk and how we try to go about it. And I'll go back to a high school math example, okay? We're going to play, I guess, an optimization game, or maybe just a math game, we'll call it. We're flipping coins, okay? And I'm going to put, the game we're going to play is that you got to flip 5 coins. If any come up tails, you fail the task, right? So the math is pretty easy on this. We're assuming independent probabilities for the different coin flips. So you find a risk of failure probability. Your risk is going to be equal to 1 minus the probability you will survive, which is going to be equal to 1 minus a half times a half times a half times a half times a half. You all can do math. I trust you all. Somewhere in the 97% range. And you can compare that to some acceptable fail tolerance, right? That's a very simple, that's one way you can aggregate these probabilities along the course of your trajectory. In this case, your trajectory is number of coin flips. It will then become your progression through your continuous dynamics for your robot. Or of course, you could seek to minimize probability of failure. I guess you just flip fewer coins if that were an option available to you. So what do you do with that information? Okay, so we're going to bring up something we love to call our failure probability function. Okay, not to be confused with the probability distribution. You'll note that that area under the curve is not one, is not designed to be one. All it is mapping two things. The x-axis is that little delta right there. That's what we call a risk source. It's some combination, some function of all your system variables. I don't care what it is. It could be a state, it could be time, it could be, it could be control input, it could be a ground reaction force, whatever you want, okay? And then on the y-axis is the probability that you will fail at any given small delta t in that risk source, okay? So that's all that is, okay? And those are probabilities. And then we're just going to take a little logarithmic operation of it, okay? We're going to morph it down. What we're going to do is take the log of 1 minus that function. You get something that looks roughly like that in my toy example. That was an example failure probability function, okay? And you'll get something that looks like that. Now, if you look at this from an optimization standpoint, you have a piecewise curve, which you can actually represent, though, as a series of linear constraints and slack variables to keep the problem actually, these constraints convex. So if you introduce a slack variable on the y-axis, some s tilde, we call it some log survival variable, and you upper bound it by those two intersecting line functions, then voila, okay? Any given probability is bounded in this space. We call this log survival space just because. And as a result, it's a convex constraint on our optimization. So we can actually add this into our normal motion planners, okay, as additional constraints. We'll have it, and specifically, you'll have that first constraint, which would say that, hey, I need my safety or my survival probability to be better than my acceptable risk tolerance. That's what that first constraint is. And the second one is just bounding those curves in order to have that convex set of constraints. So when you boil that all out, you have two different kinds of trajectory optimizations. One that's constrained by a certain acceptable risk tolerance. You could say, I want a 10% chance that I'll succeed in this task, or a 90% chance to succeed in this task, or you just minimize risk. Either one is fine. They have their strengths and weaknesses. Okay, and that's how we turn this into a deterministic trajectory optimization problem, even though there are theoretically uncertainties and probabilities involved. Okay, how you get that risk probability, that failure probability function, we'll get to a little bit later. So, all right, so let's go to just a simple toy problem. We went way back to very simple toy problems for this. Just a double integrator. I love to call it Puck World because it's a little puck that slides around. It's kind of like Grid World. And I wanted this double integrator to go from one side of the of this arena to the other, and we put a little danger zone in the middle. And my student Jacob assigned a probability that you're going to be bit by some scary dog closer you get to his little dog house in the middle there. And we just ran this risk constraint optimization saying you could either tolerate 100% chance of failure, 0% chance of failure, or anywhere in the middle. And it generated those trajectories. You can see how they become increasingly risky or increasingly risk averse just by changing that variable. And it's just a normal deterministic trajectory optimization. And as a proof of concept on a robot, we went and took it to this very simple hopping robot. And where we wanted to add a very common way that these robots fail is that they break their legs. Okay, so we bootstrapped it with a failure probability function for how much overloading a leg may break it. And we would give it we would give it higher or lower failure tolerances and see how it would behave on the robot while trying to move it as fast as possible. So this is what it looks like normally, just one of our normal nominal gates. It's jumping around probably close to 3 meters a second thereabouts. It's a simple proof of concept kind of hopping machine. And what we did then is we generated a trajectory optimization with 0 risk tolerance. And of course, it goes right up to the barrier of do not cross this. So it's a hard constraint. But then if you loosen the tolerances, you get more and more, it'll thoughtfully cross the barrier of 0 risk. And as a result, you'll get some increase in speed. Here you have all 3 different hoppers going around. You have the top hopper, middle hopper, lower hopper, and ignore the percentage values. They are proof of concept values, but the one at the bottom goes fastest. Okay, so because it's able to take more risks. But the big question in here is, how do I define a failure probability function? It's kind of the big catch here, right? And the way we try to do it is learning it in situ. All right. So how do we go about learning a failure probability function? And contrary to this image, which we all see as a neural network, I did not use neural networks. We did not do that. We wanted something extremely low shot, at least in the simplest we could go. And so we're basically talking about a series of splines and seeing what we can get away with that kind of simple level of learning. So I will give an example of what a learning operation might look like, where we're collecting data over the course of a run of your robot. This is a hypothetical robot scenario where we're going to have data points fly on the screen, where we're going to pair up data as on our x-axis for some chosen risk source that we have chosen as a candidate, and we'll log either zeros for it did not fail, or ones for it did fail. Just that simple. So as a result, you roll in all the data points, and you can see it did a couple trials, had a couple failures, right? And then what's going to happen is we're going to run just a very simple regression, convex, just with a linear spline. So simple convex least squares optimization, and then we do our operation where we just take the log of 1 minus those values, and then sort of transform all the knot points down onto this space. And as a result, you have this now convex space that you can bound a slack variable on the vertical axis, and then do a bunch of cuts. Linear cuts to get all those curves that bound the S tilde variable. So now we have this convex formulation of this problem, of this particular learned failure probability function. So let's go back to this danger zone problem. Again, just a toy problem, and we're going to, and it's the same thing where it's risky to go into the middle of that circle, but it has no idea it's risky. It's naive. So what it's going to do, and we also know for a fact that that curve at the top, we know a priori that that's going to be the best answer, but it doesn't know that. So what it's going to do is going to drive through the middle, not knowing there's a dog there, gets bit, but then tries again. It's a lot closer to the best solution, and basically can just keep iterating until it actually not only succeeds the task, it succeeds the task very close to the optimal solution. Again, very simple proof of concept here, but you can also apply it to a more complex kind of robot. So I didn't expect to be doing anything with arms, but certainly we started doing something with arms, where we decided we want to take this robot arm and move it from one side to the other, just a simple pick and place task. We weren't going to tell it anything about what a failure might be. If it in fact impacts itself, we'll say that was bad, trigger a failure. But it has no idea what's going on with its kinematics. We are planning on the double integrator level, and we have some black box controller that's doing the inverse kinematics from it. So basically, it's going to learn what is good and what's not a good safe zone from a single experience. So we'll watch that go. You can see it kind of, it hit. Oh, sad. It hit. Don't do this with the robots, by the way, guys. And then the second will go around, it realizes, hey, it regresses, that was a bad thing. It likely led to my failure, and then it goes around. All with very, the learning is of course very fast. And right now, this is technically a nonlinear program that runs in under a second. Okay, but I'm sure back in some people's minds, it's like, Dr. Hubicki, we're friends here. Christian, how are you choosing your risk sources? That's a great question. So right now, for these proof of concepts, we were just picking them as things that might make sense, and they may or may not be linear in your state variables, in all your other system variables. Okay, so wouldn't it be great if there was a way to automatically select these risk sources? That's what we're working on right now, specifically so we can get linear constraints. Because if we get linear constraints and we can have some linearizable or linearized model, boom, we have model predictive control that can run on the fly, picking up and improvising its trajectory on the go. Okay, so one of my students who's now at ATI, he decided to take this failure data and where you would potentially have different risk sources that you were measuring, and he would then plot them on. Then he would do a projection onto a line that would be defined by the centroids of the failures and the successes. Okay, so so basically showing that, hey, if you have some arbitrary potential risk sources, you can throw as many in there as you want. The projection is very efficient, and of course, and it'll give you what is effectively a basis function for your failure probability function or a risk source, right? So you could have a number of linear variables. It could be the time that's been in your task. It could have been the state 10 seconds ago. You could theoretically throw a lot of things in there. Look forward to playing with this to see what this kind of results get us. But on top of all this, there are of course some things we know that we would care about in real robot space that are not linear in our variables, such as the distance to objects, things you don't want to run into. Okay, so that's a Euclidean distance. Of course, it's not linear. Okay, however, we can linearize it by doing some nice feasible. We can convexify it with a relaxation by looking at the feasible half space over time, and we can update this half space approximation along a trajectory, and it becomes a linear in our system variables, and it makes it easy to fit into the optimization framework, which is nice. And it actually performs quite well with just a very simple. With a very straightforward task where you're trying to avoid obstacles. Okay, this is in spite of the linearization. So we chose obstacle avoidance as a test case here. Naturally, you don't want to hit obstacles generally, but this is a good test for us to be able to see if in the future we can do these distance-like metrics in this linear fashion and fit them into our risk formulation. Okay, and this actually turned out to be a pretty good indication. You can see that our little model predictive controller is pretty good at dodging around stuff in both single and multi-agent settings. We have no formal guarantees or barrier functions or the like, but it seems to work pretty well in getting around. And again, this doesn't have a risk formulation in it. It is doing an obstacle avoidance maneuver, but it's convex thanks to the relaxation. And of course, it applies to other modes of locomotion as well. Here's your walking linear inverted pendulum, which is nice. So it applies to walking locomotion as well. And this apply and we can plan around these, and so it's automatically generating these center of mass motions and foot motions. And we have controllers that we're developing that will track center of mass trajectories and foot trajectories. This is some work by my student Tienza, who has been making these operational space controllers track these desired trajectories. So the idea is we have these reduced order models do the learning, and then we fit it to and then we have these high order models track them. So that'd be fun. But these are simulation results here. In order to get hardware results, we decided to play around with some drones. Okay, so we decided to start swinging some pendulums at it, and it's pretty agile. But basically, the point here is to show that it's actually really effective. That the online MPC is pretty darn effective at dodging around this drone, dodging around this pendulum we're swinging at it. The sensing is external, to be absolutely clear. Okay, and here's a little slow motion footage of it in case you missed what was going on. So you can see the Vicon markers on there. So we decided to take that and then extend it to, hey, what if we have a robotic task where the game was tag, where you have a chase drone and an avoid drone, okay? And we use the same formulation, and it's pretty agile. It's pretty reliable at getting around these different, in this 2D setting, going around. I was very, very proud of what my students were showing this. I couldn't stop watching it. So showing that this linearization, that this convexification is pretty effective for online NPC. And it extends to 3D. That's not a mathematical challenge at all. It's more of an actual robot challenge, and that the downdraft was getting in the way of the robots. But that's a different thing. And so just to wrap up here, we were nearing the end. So now we have all these components together. We're starting to finally combine all of this with our risk learning on pieces of hardware. So this is a test we got like 4 days ago. So it's very preliminary, but basically this drone is completely naive to the world. Then we take the stick of doom and we move it to the thing, and it goes, oh, I failed. Okay, jumps down to the ground. Okay, all right, then it learned, and it's gonna go, oh, try again. We put in the stick of doom, and it's like, at least it knows, like, hey, I don't like the stick of doom. It's gonna, and we're not being very aggressive with stick of doom. This is very early in our process here. And it's just jumping around, and you'll see it kind of zips around a little bit when it feels cornered. Okay, but we have some more tuning to do. I have to say, I'm very proud of my students. They did this all on a very tight deadline for me. I'm very appreciative. So that's where we are in terms of hardware results. So I'm going to go up to my closing remarks here, because it's all ongoing, and I'm very excited where it's happening. So what's going on right now? So one, I want to point out that at this point, I think we're able to convexify pretty much everything, just about everything we need. So that way we can do all these computations on the fly, learn on the fly, replan on the fly. And I'm sure some of you are thinking, I imagine these other methods that we talked about are really helpful. Do we really want to have to run our robot into grandpa to know it's a bad idea to run into grandpa? No, we do not. But there's no reason you can't put CBFs, control barrier functions, in. You can't do that. There's no reason you can't do that in the same optimization problem. You can even put your chance constraint methods in there. Anything that can fit in a constraint in an NLP or a convex program can fit in this as well. Not that it should play along nicely. And what gets me most excited is this idea of going from naive to performing like close to a blink of an eye, or at least within the attention span of a human watching the robot. To be able to give it a task that it might not even know, but then all of a sudden you tell it failed at the task. Then it starts to regress, oh, what did that mean? And what I want to do is take our Cassie robot and have a drone come up and plunk, and we tell it you failed. And then it realizes it has to play tag, and the drone is it. And so that's the big picture of what I want this framework to do. And I really appreciate all of your time, and I'm happy to take your questions. Have a wonderful day.
You have time for one or two questions?
Thank you. An excellent talk. I want to ask about the probabilities when it comes to the sequential evaluations of your function.
Yes.
Right. They're not independent point flips.
Mm-hmm.
So do you handle that, or does it get in your way?
So far, the things are pretty impactful. Like, I'm assuming hitting the robot will end probably the trial. But you are right, and I think that I wish I had. This is a very near-term next step, other than adding some noise into the uncertainty to show that it will be able to handle that. That's probably the next step. But that you can have interesting interactions, but with the probabilities over time. It doesn't need to be uniform. In fact, you could have contingent probabilities, I believe, add up in this framework. Okay, check on me in a couple months, hold me to it to see if I've done the math yet. But like, you're absolutely right. Those assumptions will matter in the long term. And so maybe having a vocabulary of these assumptions that it can sift through on the fly would be important.
Yeah, sounds great.
Thank you very much.
Cool. For the sake of time, let's move on to our next speaker.
Thank you all so much.
Thank you. Let's thank Christian as well.
Thank you so much.